Hello, statistics students. So I want to walk you through one of the examples from chapter 13. This is the last chapter we're going to do this semester. It's on two-way ANOVA, and we're going to walk through the example with the grazers and the seaweed. And this will be relevant to your two homework problems for the week, which are posted as homework 14. They are numbers 17 and 19. I've uploaded the code for this example as well, and I sent you the link for the PowerPoint. So we're going to kind of walk through this PowerPoint. It's on two-way ANOVA. In two-way ANOVA, the idea here is you have a quantitative response variable. In this particular example, we're looking at how much of the seaweed has regrown since these grazers have eaten it. So that's a thing you can measure, so it's quantitative. And you have categorical variables. And this is actually something we looked at a little bit when we looked at the moth case study. We had a categorical variable about the herbicide treatments. And anytime when you have two categorical variables, you're in a two-way ANOVA situation. Two-way meaning there's two categorical variables. And it turns out you can actually analyze this in the ANOVA framework with an F test, like we did with the ANOVA examples, or you can analyze this as a regression. And mathematically, they're equivalent. The regression gives you T statistics, and mathematically, T statistics squared give you F statistics, which is what you use in ANOVA. So if you take a more advanced probability and statistics class, you can actually prove that it's essentially the same thing. The framework for doing it in R makes it so that using one approach or the other can be a little bit more practical depending on your situation. So I want you to be able to use either approach, knowing in the back of your mind that they're mathematically equivalent. So let's see, that's slide 2. On slide 3, we're checking out the seaweed grazer situation. So the thing is, there's lots of seaweed. It grows where there's like tide pools near the ocean, and all these creatures eat it. There's limpets, which are like these little, they're like little coney things, and they crawl along and they eat seaweed. And there's fish, there's small fish, there's big fish, there's like all sorts of other things. So there's also this situation where not all the places that the seaweed grow are the same. So if you go on to slide 4, you can see in these particular places, there's like places where there's green seaweed and places where there's brown seaweed, and there's places where there's more seaweed and less seaweed, and the further away you are from the ocean, the less the waves come up. And if you have like smooth rock, there might be less seaweed attached versus like vertical rock surfaces that not very many people walk on might have more seaweed. So you have this situation where regardless of who's eating the seaweed, there's like more seaweed and different kinds of seaweed in some places than others. So they wanted to set up this experiment in multiple different places with the idea that if they set it up in some places that have more seaweed and then some places that have less seaweed, they'll be able to see whether the effects of the grazers are like consistent depending on the different kinds of seaweed habitats. So that is what this blocking variable is. So blocking is a way to account for variation that they're not really interested in. They're really interested in how much the different kinds of grazers affect how well the seaweed grows. And they have to take into account the fact that there are a lot of other reasons that there's more seaweed in some places than others, and that is the blocking variable. So if you look at the header of the data set, you will see the amount of seaweed, which is the cover. You will see the block, which is like where it is, and you'll see the treatment. Now the treatments are super complicated. So let's go on to slide 5. The control is called L, little f, big F. And that means limpets are allowed in, little fish are allowed in, and big fish are allowed in. So the letters here indicate what kind of grazers can get in to eat the seaweed. So under normal circumstances, if they weren't messing with it, everybody would be able to get in and eat the seaweed. So there would be limpets, little fish, and big fish. And they put a little cage around it to sort of designate the area. And limpets crawl along the rocks. They're like physically attached to the rocks. They have like a little foot that attaches them. So if you put like a strip of nasty grossness, they can't like crawl over that strip. So the little f, big F treatment doesn't allow limpets because they can't crawl over that thing. And then they can also put a coarse net over the seaweed, so then little fish can get through the net, but big fish can't. Or they could put a finer net so that neither little fish nor big fish could get in. And then they can do like the combination of the strip and the big net or the little net. So then they have all these different combinations. They have 6 possible combinations of treatments here. If you just look at the graph on slide 6, we're looking at which kinds of animals are present along the x-axis and how much seaweed is still there along the y-axis. And then I made it so that the labels, like it says like B4, B3, so in each block there's 2 replications of the full experiment. And what we can see just by looking at this is it seems like there's more seaweed anyway in block B4. Like everywhere you look, pretty much B4 is like near the top. And there's less seaweed in general in block B1 for like whatever reason. Maybe that's a place where they set up the experiment where there was less seaweed to start with. It does seem like where there's all the grazers, the L little f big F treatment, that is where there's the least seaweed. Okay. It looks like normality is going to be an issue. It looks like there's more. There's also an equal variance issue. Like the smallest treatment has the least variance, and the treatments with the bigger means have the most variance. I don't love this graph. So on slide 7, this is a cool graph. It's using a different kind of graphing program than you've used before called ggplot. The code is on lines 13 to 21. But I can see how different the treatments are across the blocks. So along the x-axis is the blocks, and along the y-axis is how much cover there is of the seaweed. And it's averaged across the 2 replicates at each block. So one thing to notice here is if you look where my little pink arrows are, the difference between, the control and the small fish in block 2 is much smaller than the difference between the control and the small fish in block 8. That makes me wonder whether the effect of the small fish depends on the block. That would be an interaction where the effect of one thing depends on the other thing. So that would suggest that I don't always have the same consistent effect of the grazers. In some blocks, the grazers have more of an effect than others, which could totally happen. It could be that like limpets don't like to graze as much on steep surfaces, or they don't like the kind of seaweed that grows on a particular kind of rock as much. And then you wouldn't be able to say something in general like limpets graze this much, because it actually depends on what kind of habitat you're in, how much limpets graze. But I'm also worried about the equal variance situation here. So I'm going to just look at a residuals plot from a full model here. So that's what's on slide 8, and it's really crappy. So I look at this and I see in the middle of the plot, there's like super high variance, and on the ends, there's super low variance. I don't love that. It doesn't meet my equal variance assumption. So I'm going to try some transformations. So if I go on to slide 9, I'm going to try the log ratio. So what I have here is the ratio of cover to what's not covered. So cover goes from 0 to 100%. So if like there was 90% cover, there'd be 10% not covered, and the ratio would be 90 divided by 10. And then I'm actually going to take the log of the ratio. So that's my transformation. That's actually not a very uncommon transformation. It's fairly typical whenever you have cover, so it's a percent, and it goes from like 0 to 100% or 0 to 1, depending on how you express it. You're going to have issues with normality because things that are near the bottom like hit against 0, and things near the top hit against 100. And it's really hard when you have a hard upper and lower bound to get normally distributed data. So that's why I'm doing this transformation here. And I'm just going to look at the data. So on slide 10, I have that same graph again, but now with the log ratio. And what I see here is the differences of the treatments between the blocks are much more consistent. So if you look at my little pink arrows in block B2 and B8, the difference between these treatments, it's still not exactly the same, but it's less exaggerated than it was before. So there's less evidence of the effect of the grazers depending on the block here. That's cool, but that's not really why I did the transformation. The real reason was to try to deal with equal variance. So we can look at the residuals from the full model in slide 11, and what we see is it's still not perfect, but it is much better. The spread of points around the horizontal red line in the middle is more even across the full range of the data. Okay, so now on slide 12, I can run a two-way ANOVA. This is awesome. This is the similar code that you used to run ANOVA when you did that. I am including block times treatment, which means I'm willing to consider the possibility that the effect of the treatment depends on the block. And the code is lines 35 through 36. What I see here is my ANOVA table, and I'm looking at the second to bottom line of the ANOVA table, this block colon treatment line, and my p-value is 0.12. That suggests that the effect of the treatment does not depend on the block. That's not a very convincing p-value. That's awesome. That means that limpets have more or less the same effect regardless of the block. Small fish have more or less the same effect regardless of the block. Big fish have more or less the same effect regardless of the block. That's cool. So I don't have to include that in my model. I can drop it from the model and rerun it. So slide 13 says that. Slide 14 is what happens when you drop it from the model. You get a simpler model. You have one line that tests the effect of blocks. The p-value is wicked small, so the amount of seaweed between blocks differs. Another line, treatment, that distinguishes between the treatments. The p-value are really small, so not all the treatments are the same. All right. This is the same as running a regression, but an annoying thing here is when we looked at the treatments, the p-value just told us that not all the treatments were the same. And now we have this situation where we could do post hoc tests, like you could do a Tukey post hoc test as you've done before. But that's kind of annoying. It would be simpler if we could just look at all the treatments with the limpets versus all the treatments without the limpets, or all the treatments with the small fish versus all the treatments without the small fish. Those would be contrasts, which you've done before, but they're simpler in a regression format. So let's go into a regression format. On line 16, I'm running the full model as if it's a regression. So actually, the model that I'm showing you on slide 16 is mathematically equivalent to the model that I showed you on slide 12. Even though it has way more lines, instead of looking at all the blocks together and whether all the blocks are the same, it has whether block 2 is different from block 1, and the p-value for that is 0.3. Whether block 3 is different from block 1, and the p-value from that is 1.7 times 10 to the negative 5. Whether block 4 is different from block 1, and so on. And then it has the treatments, whether treatment L is different from treatment C, and the p-value is 0.003. And then it has every interaction. So instead of combining to ask whether all the treatments are the same, it's asking whether each treatment is different from the control, whether each block is different from the first block. So it's a more complex presentation of what is mathematically an equivalent model. So I still want to know whether I can drop all these interaction terms, like the bottom bajillion lines are the interaction terms. There's a whole bunch of them. And I have to do an extra sum of squares F test to test this. So I'm going to do that on slide 18. And what I do is I do model 1 is just the block plus the treatment. And model 2 is the block plus the treatment plus the interaction. And then I'm going to do an ANOVA comparing the two. And my p-value is 0.12. You will notice this is exactly the same p-value I got when I ran this as a simple two-way ANOVA on slide 12. So I just did this way more complicated model and got exactly the same thing, which is what I told you would happen. ANOVA is the same as regression in the guts of it. That's really cool. Okay, so I can run the simpler model. I can get rid of all those interactions. That's what I do on slide 19. This is actually the same model as, which one? Slide 14. So it just has all the terms spelled out. Instead of looking at all the blocks together, it's comparing each block to block 1. You'll notice now that we're in the regression format, we have an estimate of r squared. So we're saying we think that the blocks and the grazers explain about 83% of the variation in the log ratio of the seaweed cover. If I want to know whether all the treatments are same, here I have just like treatment L compared to the control, treatment LF compared to the control. I don't have a single p-value that tells me whether all the treatments are the same. So to get that, I would need to do an extra sum of squared F test. I do that for both block and treatment here on slide 20, and what I find is that both block and treatment are significant. So my p-value for treatment is this first one, has an F statistic of 30.368 and a p-value of 2.2 times 10 to the negative 16. You'll notice this is the same as on slide 14. Then the next part is the p-value for the block. The F statistic is 54, p-value is 2.2 times 10 to the negative 16. This is also the same conclusion as in the two-way ANOVA on slide 14. That's awesome. So, on slide 21, the ANOVA format is pretty and clean. It's great for testing. Are all my treatments the same? Are all my blocks the same? It was definitely the cleanest cut. Instead of like 20 some odd lines of code and output, you had like 3, which makes life a lot easier. The big problem with using two-way ANOVA instead of regression is when you have complex follow-up questions, and regression is a more flexible tool for answering those questions. So on slide 22, we can see there's all these other questions about the limpets and the small fish and the large fish. So we end up having to make new variables for whether there's limpets, yes or no, whether there's small fish, yes or no, and whether there's big fish, yes or no. So I did that in the code in lines 57 to 59. And we also want to know specifically, do the effects of limpets depend on whether there's small fish? Do the effects of limpets depend on whether there's large fish? So these are things I can follow up on more easily in the regression format. So let's see. If we go and we look at those models, I can look and see whether there's evidence of an interaction. I do that by comparing the model with just the limpets, the small fish, and the big fish versus the limpets, the small fish, and the big fish. And then this raised to the 2 doesn't actually mean squared. It means consider all the possible two-way interactions. The p-value here is 0.72, so there's no evidence of an interaction. So the effect of the limpets doesn't depend on whether there's other big or small fish. If we go to slide 25, I can look at the effects of all the blocks. I'm not really interested in the blocks, whatever. They're just the natural variability of how much seaweed there is. But then I can look at these last 3 lines of the model, whether there's limpets. The p-value is 2 times 10 to the negative 16, so limpets do matter. Small fish matter, their p-value is 0.00965, and big fish do matter. And here I get an estimate of the slope. So the estimate of the slope for the limpets is minus 1.82. The estimate of the slope for the small fish is 0.39, and the estimate of the slope for the big fish is 0.61. This is cool because I can estimate how big of an effect each of these grazers has on the seaweed. So now I was on the log scale, so I'm going to have to do some like exponentiation stuff, which is what happens on slide 26. So I take my coefficients. I'm only really interested in those last 3 because that has to do with the grazers. I do e to them. I get 0.16, 0.67, and 0.54. I can get a confidence interval for them. So then I can say the median seaweed regeneration ratio with limpets is 0.16 times the median seaweed regeneration ratio without limpets. My 95% confidence interval is 0.13 to 0.2. Or I could say the median seaweed regeneration ratio with small fish is 0.67 times the median seaweed regeneration ratio without small fish. And I can get a 95 confidence interval with that as well. 0.5 to 0.91. Awesome. That's really what we wanted. We wanted to be able to say how big of an effect does each kind of grazer have on the seaweed. If you look at my original plot, which is on slide 27, one thing is it's really hard to visually tell what the effect of each treatment was on this plot. Like, I can't look at it and be like, oh wow, the limpets had like a way bigger effect than the small fish. Like, I don't know about you, but my brain is not able to get that information from this plot. So looking at the partial residuals plots can give us a lot more useful things about that. So towards the end of the code, I required the car package, which allows us to look at these partial residual plots. And on slide 28, we're looking at that. So the first thing is we look at the effects of the blocks after accounting for the different treatments. And we can see a box plot kind of showing which blocks are higher than the others. And then the next one, we looked at the effects of the limpets after accounting for the blocks, the small fish, and the big fish. We can see that there's way more seaweed whether there's not limpets. Then the next one looks at the effects of the, small fish after accounting for the limpets, the blocks, and the large fish, and there's not nearly so much of a difference here. So the small fish are statistically significant in their effects as grazers, but not nearly so much as the limpets. And then you can see that the large fish, which are the last one, are sort of intermediate. So this is useful because we can say, oh, the limpets are the grazers that have the biggest effect on the seaweed. The small fish still have an effect on the seaweed, but not nearly so much as the limpets, and the large fish are sort of intermediate. So that's all we got for what I want you to know from chapter 13. There's plenty of extra reading you can do, and I think you should be ready to tackle the homework on the topic. All right, bye.